FG and 21 on the PG. That's a total of 39 questions, so there's a heavy emphasis on this topic. Concepts and definitions are things that you would find on the FG for the most part. And looking at things like water quality, aquifer yield, hydraulic properties of an aquifer. The well construction and site investigation is more typically the PG type question, although there might be some questions about wells. But in terms of where to put them, setting up your investigation, that sort of thing is going to be more of a PG type question. And then environmental geochemistry is going to cover the contaminants, their sources, geochemistry, and that, again, more of an FG type of approach, and remediation is going to be more of a PG. Once we identify what's there, how do we take care of it and remediate it? So looking at a definition, vadose zone. The vadose zone is measured from the ground surface to the water table. It includes an unsaturated zone and saturated zone. So when the terms unsaturated zone and saturated zone are used, it's not always clear what that refers to. Is the saturated zone measured from the water table? Well, it does include the capillary fringe, which is saturated. So rather than those terms, I like to think in terms of pressure surfaces, and above the water table, the water is less than atmospheric pressure. And then at the water table, it is equal to atmospheric pressure. And below that, it is greater than atmospheric pressure. So just be careful when you see these terms unsaturated and saturated. Another definition is aquifer. And the part of this definition that we don't often think about is the economic quantity that it can provide. But within the definition are the aquifer properties that we're going to look at in more detail. The storage properties depend on the porosity. The transmission depends on the hydraulic conductivity. And the flow is based on Darcy's law, which the very simplest form of that law. And so we're going to look at some equations, maybe a dozen or so that you should know, but there's not a heavy emphasis on equations on the exam. So there might only be one or two that you would need to know, depending on the question on the exam. You also don't need to know partial differential equations. So that is a relief for many of you, I'm sure. It was for me. And so let's look at these in more detail, starting with storage. Storage, we said, was based on the porosity, which is the volume of voids to the total volume of the rock or soil. Now, in engineering geology, we don't want that void space to be filled with water, because then if we're trying to get compaction, it's not going to happen. And so the void space in hydro is, we're assuming all of that is filled with water. And the ability of that water to move is based on the effective porosity, that is, how interconnected those pore spaces are. So if you think of a clay is very porous, but it's not permeable. There's not that connection between the pore spaces so that the water can move through it. And we say that the effective porosity is equivalent to the term of storage for unconfined aquifers, which is specific yield. And so looking at the porosity equation, it's the volume of water drained under gravity to the total volume. So if I have a sponge that is saturated and I put it on a clothesline and let it drip, 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 drip and collect that water, That's going to be my specific yield. There's still going to be water in that pore spaces in the sponge. So that is my specific retention. So if you add the specific retention plus the specific yield, you get a measure of the full porosity. Now, in the case of a confined aquifer, water is yielded by the ability of the mineral framework to relax enough to give us the water. And so the process is based on the specific storage and the saturated thickness of the aquifer. So whenever we see a value of storage that's very low, that is going to be for a confined aquifer. And that would be as if the water is yielded by squeezing that mineral framework to get out that little bit more that it is within the sponge. So unconfined or specific yield of unconfined aquifers is 10 to 30%, and the storage for confined aquifers is very, very much smaller. Anything in between is probably a leaky aquifer. So another way we can look at this equation of porosity is to take the volume term, and we're going to break that up into an area, a basin area, and a vertical change in head. So we can measure a drop in water levels and calculate the volume of water that is lost from storage. So if we have a negative sign here for storage, that means that our water level has dropped. So this is an instance where it's important to pay attention to that minus sign. If there's no minus sign, then our storage has increased. So this is just another way of taking that porosity and coming up with another equation. We can take that information and put together a water budget. And a water budget is looking at a basin, measuring the inflow and the outflow, and coming up with a net value of storage. And the inputs depend on four things: the natural inputs, precipitation, which is all positive, evapotranspiration, which is all negative, runoff. So we have to think of runoff in minus runoff out for the net value of runoff, and underflow, which is groundwater flow. Net value in minus out to give us that value. And it makes this nice Peru equation that we can remember. Now, there's a lot more going on in a basin. We have people pumping water. They're irrigating. Do they use imported water, or do they use water that they've pumped from the ground? They have on-site wastewater treatment systems. So instead of plumbing. So if they have plumbing, maybe it's going to take the fluids off of the basin. So looking at all of the potential sources, and a big one is the vegetation. And so you have to look at the area that's covered by vegetation, what those water needs are, and this is particularly important for agricultural areas. Certain times of year it takes more water than others. Do you have drought-tolerant plants? All of that has to be factored in to get a true picture of a water budget. Now, you're not going to have to do one of those complete water budgets, but you might have a piece of it that you have to do. And often these kinds of problems require you to change gallons to acre feet, and do some conversion of the units. So just get comfortable doing that sort of thing. Second property of an aquifer is its ability to transmit water. And the transmissivity is based upon the hydraulic conductivity K and the saturated thickness B. And in our English system, the units can be gallons per day per foot or feet squared per day. This becomes important when we're doing pumping tests. So just tuck that away for now. And then this section here is a reminder that our hydraulic conductivity is based not only on the material, clay, silt, sand, gravel, but it's also based on the fluid. When we have water, we tend not to think about the water. We think geologically, think about the material. But if we have contaminants, are those properties of weight and viscosity greater or less than water? So that's going to act a little bit differently and impact the hydraulic conductivity of those materials. So I always think of this as, this is why geologists need to be involved, because we know the material properties, maybe not the fluid properties as much, although I think we're getting there. And so it's important to have both of those things squarely set, that it impacts our hydraulic conductivity. Its units are in gallons per day per foot squared in the English system, and it turns out that that is actually a velocity. So I often like to convert that to feet per day so I can clearly see that it's a velocity. And then a Mainzer is just as it originally was defined, a gallon per day of flow through a square foot under a gradient of 1 at the field temperature of 60 degrees Fahrenheit. So a gallon per day per foot squared is just a Mainzer. Here's a table in your study manual that shows the values of hydraulic conductivity. If you have worked in the oil industry, you're probably more familiar with Darcy's, which is the intrinsic permeability, the material properties. And if so, then you'll note that to get the hydraulic conductivity value, it's 2 orders of magnitude higher. But if you haven't worked in the oil industry, I would just concentrate on this big K column for these materials. And you'll notice that we've added the Unified Soil Classification System symbols that Lisa will talk about tomorrow, because they might just give you those symbols and without a description of what the material is. So knowing those and some representative values can be very helpful. You might have to choose a representative value. I wouldn't worry about fracture permeability because it can vary, depend on, you have to do a more detailed analysis of where the joints and the cracks are, and that's going to be beyond the scope of the exam, so we don't need to worry about those. Okay, the third property of an aquifer is its ability to the water to flow. And based on the Darcy's law of flow equals hydraulic conductivity times a gradient times an area through which the flow occurs. Q equals KIA. Now, if we look at the cross-sectional area through which the flow occurs, if you hold up a piece of paper, and perpendicular to that is the direction of flow, we can come up with the area of that piece of paper by a width, and on the vertical side, our saturated thickness B. B times W gives us that area. And we can substitute that in for the area. We can substitute for hydraulic conductivity, which is T over B, and the B's cancel out, and we're left with transmissivity times a gradient times a width. And these are the two forms of Darcy's law that you may encounter or need to know. I never saw this before I took the certification exam in California. I had to go back through a number of older textbooks before I found this, and where'd you get that? So it's important to know. The gradient is defined as the change in head that occurs over a length. So here's where I like to think about the terminology that we've already talked about in structural geology. Structural geology, points of equal elevation on a bed are the strike. In hydrogeology, they are equipotentials. Perpendicular to strike is the dip direction. Perpendicular to the equipotential is the flow direction. In structure, tangent of the dip angle is the rise, the vertical, over the run, the horizontal. In hydro, we don't care about the angle, so we're just looking at the ratio of the rise, the vertical, to the run. So it's the same concepts as in structure, but just using different terms. And then finally, if we want to come up with an average groundwater flow, we have this hydraulic conductivity times the gradient divided by the effective porosity, which we said was equivalent to specific yield of our unconfined aquifer. So it doesn't get more complicated than that, thankfully. A couple more terms. This is in the back of your course notes, page 9. And let's just take a moment and look at this in more detail. We have curved lines, we have straight lines, we have a groundwater barrier called out here. We have two values at each of the points. The top value is for the unconfined aquifer elevation, and the bottom is for the confined aquifer elevation. And those are minus, those are negative, below sea level. Okay, so this is not topography, these curved lines. But what we have to realize is that in an unconfined aquifer, it's going to mimic the overlying topography to a more subdued extent. And when we look at the values, we have 185 up here and we have 160 down here. So the flow direction is down to the south. And I've put in a bunch of arrows perpendicular, which show that the water is going to converge into this central part, just like if we had a swale and the water was coming off the sides and into the midsection. Whenever we have a confined aquifer, it's going to be contoured with straight lines. And without this groundwater barrier, we'd be tempted to put a whole bunch of contours in between the minus 64 down to the minus 101.4. Same thing over here. But we called out a break. And this is often how we find faults in the Western US, where we have the water piling up on one side and not being able to go across the barrier for some reason, whether the lithology, whether there's clay gouge, fault movement, something like that has happened, creating that barrier. So we have three aquifers. We have the unconfined aquifer that is modeled with the curved lines, and then we have one going to the northeast, southwest, and then one going trending east-west. The opposite of convergent flow is divergent flow. So if you think of the nose of a ridge, the water's going to fall off in almost 180 degrees as it comes off that nose. Okay, so question, are seepage velocity, specific yield, and discharge synonymous terms? No. Seepage velocity and groundwater velocity are synonymous. Specific yield is the storage of an unconfined aquifer. And discharge relates to Darcy's law, which I didn't get into that aspect of Darcy's law, so I don't think you need to worry about discharge. Okay, so now we have a problem that we're going to figure out the gradient and direction of flow of the confined aquifer. And since there are two of them, we're going to choose the one that has the largest surface area. Gradient is the rise over the run. And the difference in elevation is minus 100 to minus 102. So we have 2 feet of elevation change. And we have a distance here of 541 feet measured at the scale of the map. So whenever you do one of these, you want to take the longest run that you can across your map. And I like to divide out the units so that it is dimensionless. And then I'm going to put in a tracer into one of the wells and see when it shows up at a down gradient well. The things that are suitable for tracers are it's easy to use and detect, both in the field and the lab. It's non-toxic, doesn't react, doesn't adsorb onto the soil, and it's cheap and readily available. And the things that meet all of those criteria are the chloride and bromide ions. So they're the most widely used tracers. But then for your particular needs, if you're working in karst, often they use fluorescent dyes like rhodamine or eosine or something like that. And sometimes salts are used. I would be careful about that, particularly in a drinking water aquifer. But you could use your electrical conductivity methods to measure that. And then looking at things like the O16 to O18 ratios. O18 is found in older water. O16 would be newer. So whatever a ratio there could be worked out to see what your groundwater movement is like. And then the microspheres. For this, if you have a reservoir, you can use those plastic spheres to prevent evapotranspiration. But you could also use it in karst, where you have disappearing streams, and you count the number you put in and what you get out of your output, and sort of get an idea of where the water is going that way. So you can use a lot of different things in that way. So the question is to please repeat about the relationship between O16 and O18. O18, it's been around a lot longer. So that isotope, there's more of that isotope in the older water. And O16 is generally what's in the atmosphere and what comes into the groundwater. So whatever that ratio is, I guess you'd have to have a current standard, and then whatever the difference would be as you're measuring could give you an idea of how to use it as a tracer. Use your geochemistry. Okay, let's do a groundwater or seepage velocity question where we have that equation here, Ki over N sub E. And we're given the hydraulic conductivity, we've calculated the gradient, and we're given the effective porosity. So we end up with something in gallons per day per foot squared, which I said, I don't like that. I want the feet per day. So I'm going to convert that. And I need this conversion factor. It's in a red box because it was not given to people on a previous exam. And that's really not fair. So I want you to know it. It will come in handy in another way that we'll get to a little bit. But I would also make a comment on the comment page in your test book. Why was this conversion factor not given to us? Because I don't think it's right. Anyway, so we have the velocity now. We put this tracer into borehole 19, and we know that the flow direction is to the north, so it's going to be found in borehole 12. How do we get that time? Well, if you have these units of feet per day, we have the distance, and the time is our distance divided by the velocity, right? So velocity is distance per time. So measuring that distance at the scale of the map gives us 131 feet, and dividing by our velocity gives us about 5 months for that tracer to be found in borehole 12. Okay, so here we're going to cover some aspects of putting in a drinking water well. And one of the first things that we're going to consider is what kind of casing should we use? Cement would be used for a deep well, petroleum well perhaps. Fiberglass is very expensive. So depending on your water quality, you might want that. But typically plastic or steel are used. We want to put the well screens, the openings, where we have the highest hydraulic conductivity. And we want to think about optimizing those openings so that we can effectively develop the well. The thing is that we don't want to have so many large openings that we draw so much of the fine material into the well, because it makes the development process so much harder. And it also could create a situation where you have some turbid flow that is going to be more erosive, and you have higher entrance velocities, which can erode your formation or your filter pack. So here we have 3 examples of the kinds of screens that are used typically. The first one is the wire wrap, and this one prevents the formation from clogging the well. It comes in a variety of sizes. The shutter screen is this one. Looks like a shutter. It has a more limited open area, and it's often used in artificially packed wells. It has good strength because it doesn't have as many openings as something like the bridge slot. But it's not as easy to develop in the naturally packed formations. And this bridge slot, there's a lot of different sizes, and it has a high intake area, and it's cheap, but it doesn't always have the strength, so it may collapse. Filter packs. This would go into the annular space around the well, and whether or not you need a filter pack depends on what the formation is. If you have homogeneous, fine grain materials, you need a filter pack. And anything like a coarse grain material, non-homogeneous, you can get away without using a filter pack. And I've done that with a number of wells that I put in for a water district where we were interested in understanding the relationship between the stream and perk ponds, where they were trying to perk the water into the ground. And certain times of year when the creek had water, that could provide water into the perk ponds. But when the water wasn't flowing, the perk pond levels were higher than the creek levels, so that could, the water could flow the other direction. So when we looked at the formation fluids, we had a lot of, not fluids, formation itself, we had a lot of stream gravels, and it's very heterogeneous. So we decided not to use filter packs so we could sort of see the natural situation. And the goal here is not to have so many fines being drawn into the well that can damage your pump or impact the development process. So depending on your local jurisdiction, they're going to have some rules about percentage or how many parts per million to draw in. And so I'm just going to choose 10% of the fines to bring in so that we can select a screen slot size that will retain 90% of the filter pack. And one of the ways to get the filter pack gradation that you need is to draw a grain size distribution curve. And then you're going to plot two more curves, one on either side of that. So you either multiply the size of those of the formation by about 4 times, and then you take about 1/6 of the formation side and draw a second curve. And so your original grain size distribution is going to be between those two curves. And then you're going to go to the filter pack store and choose a gradation that falls in between those two parameters, that those two curves that you've generated. You want to make sure that you're using siliceous grains and they're well-rounded, they're not calcareous. And you want uniform gradation of those siliceous grains. You're not going to have to do this for the exam, but I just wanted to put that in there as a way to get that filter pack gradation. Okay, where are you going to put the pump? A lot of people put it at the top of the well screen and then move on. I want to optimize it because I don't want to use more energy to lift the water from that point all the way up to the surface. I don't want it so high that if I draw down the static water level, it's below the pump. So someplace in here is where I need to put the pump. Now, when we run a pumping test, we end up after 24 hours with this thing called specific capacity. It's the ratio of the pumping rate to the drawdown that's measured in the well. And typically what happens is the more you pump at the higher rate, the higher the drawdown. So if we were to draw down 14.3 feet and put the pump there, that if we changed our pumping rate to 200 gallons per minute, we might draw that below where the pump is located. So that's not a good place. We need to apply some sort of safety factor. And the safety factor is equivalent to 70% of the available drawdown. Available drawdown is measured from the static water level to the top of the well screen. And in this case, we have 180 minus 50 or 130 feet. And 70% of that is 91 feet. So drawing down 91 feet puts the pump about here. And that will optimize its placement. Then we need to develop the well, because we could have drill cuttings or mud cake that's accumulated, and we want to increase our well production and make sure that we disinfect the well. So the kinds of well development techniques are mechanical, by over pumping or backwashing or surging, or chemical, using an acid wash. Now, the disinfection is really important because we don't want to introduce bacteria or viruses or protozoa into our drinking water. So we use a chlorine solution, and we have to look at the pH, because if we have high pH, then we need more chlorine. And lower pHs, chlorine is corrosive. And we use household bleach as our main method of disinfecting wells. So we're looking at about 5.25 to 6% available chlorine. What about swimming pool chlorine? Well, if you look at the chemicals that are in swimming pool chlorine, they're often things like algicides and fungicides, and you don't want to be putting that into your drinking water well. If your swimming pool chlorine meets the standard, which would be on the outside of the packaging, then it would be safe to use in a drinking water well. So I would read those labels very carefully, but chances are this swimming pool chlorine is going to have too much of chlorine percentage for you to be able to use it if you didn't have household bleach. The calcium hypochlorite is another source of chlorine, but as tablets, they don't always dissolve completely. So you might have some variation in the percentages of chlorine. And then finally, you need to put in a 50-foot minimum sanitary seal. And this is pretty standard across the US, although there's no standard. But this is often what is practiced in most places. There's no national standard on well construction. Question is well construction on the FG? Probably not. You might be asked one aspect of it, but probably not going to be on the FG. Now, how do we protect our well from contaminants? You might see the term wellhead protection. Now that all of the states have EPA approved plans for their drinking water wells. They've moved on to the source water protection. And what we're looking at is to protect the area that could contribute contaminants into the well. There are a couple of acronyms that you'll need to know: the zone of contribution and the zone of influence. The zone of contribution is the area that recharges that well. So if I look at a cross section, I have the divide and the water flows down into the well. Now, when we start pumping, the water that normally would continue moving down to the right on the lower side of this well is now being drawn back into the well. So that's the zone of influence that we have there. So both of those things are what we need to understand. So they might use these acronyms, and so you need to know what they are. Water quality is really important. And we have water with differing pHs. And with a low pH, we can cause corrosion of the well screens. And a higher pH, we get the formation of incrustations. So I want to look at the graph that shows these pH values. It depends on the alkalinity. So when I'm talking about this, I'm looking at this part of the curve out here before it rises asymptotically. So everything up below 7 is going to be corrosive. And then once we get into low alkalinities, you can see up to 8.5 can be corrosive. Everything above 7.5 in this area is going to give us the scale or the incrustations. So take a look at that. And then we have iron bacteria. Iron bacteria can be present naturally. They convert ferrous to ferric iron, and as they do that, they make these threads and gels and slimes and destroys the water quality. So you want to know if they're there, because you can deal with it. You can mitigate it with bleach, but you don't want it to get so bad that you then have to take your drinking water well offline while it's being cleaned up. So it's always important to know what's there first so you can deal with it. And then once we're finished with the wells, it's important to destroy them properly, and we have no national standard on this. So as I looked at different places across the country, we had 2 different methods. We could remove all of the debris, the hardware, before we put the seal in, or we could drill out the casing and backfill it, or we could pressure grout it in place, usually using neat cement, which does not have aggregate, and that could make it bridge on itself, creating void spaces there. You don't get a good seal. So either backfilling or pressure grouting it in place. Okay, dating groundwater. This is being used more frequently these days, and what we want to get out of this is the age and where that age occurs in our aquifer. We can use different things. If we are using things that measure the young ages, they are things put into the atmosphere at known times in known amounts. So tritium, CFCs, and krypton 85. And if you think of the hydrologic cycle, They're up in the atmosphere, and it rains, comes down to the ground, seeps through the ground, eventually gets into the groundwater. So that's going to give us a young age. If we're using carbon-14, that's going to give us an old groundwater age. And that is most frequently used because we have a lot of carbon-14 labs that can date, as opposed to using silicon and argon in very specific situations. And then the very old groundwater, we would probably use helium because that also has more labs than the other methods here. And so it's a little bit cheaper. So now if you're a water manager and you get an old or a very old groundwater age, what would that tell you? Well, you're not getting recharge. And that would be a big concern because it would mean that you're mining your water source. But what we find often is a range of ages in an aquifer. So that can tell you where you're getting the recharge, because you'll have the young ages there, where it's mixing, where it's moving. So you can follow contaminant pathways a little bit more easily if you have some good dates. So that can give you a really detailed picture of the aquifer, and you can manage it more carefully with that. Sustainable yield. This is a term, it used to be called safe yield, and the term was used in the sense that if I pump at the same rate that I recharge, that's going to be safe. But thinking about our budget, remember we have underflow in minus underflow out. There's a net value. And we might put in a lot of water, but it might all leave our groundwater basin. So the recharge rate does not equal pumping. It's some percentage of our recharge is our sustainable yield, 40% on average. And for a more detailed discussion of this, you might want to go to this website to understand it more fully. But the thing about this is that we have a lot of different pressures being placed on our aquifers. And so if we're looking at the technical aspects, then yeah, we could have 10 to 70% of recharge as our sustainable yield. But we also could have political definitions or economic or even court defined definitions, which may not be based on good science. And one of the things here in California, we were one of the last states to come up with groundwater monitoring and groundwater plans. And so our definition of sustainable is a little different. It's measured over the implementation horizon, which I think is about 20 years. So I don't know, in 20 years we might not even have that water. But I'm just wanting to point out that it's something that's kind of a fluid definition, and make sure you understand that the recharge does not equal the pumping rate. And if you hear people talking about that, then they are in error. Okay, lab and field investigations. One of the sampling methods is for rickrock groundwater monitoring wells, and it's called the standard or well volume method. This is where we will purge at least 3 well volumes and no more than 6. As we do that, we're sampling these parameters. They stabilize in this order, and once they've stabilized, then we can take our sample. And where we have the low yield wells or turbid water or fractured rock, we can't use this method. There's another procedure for sampling in that situation. So given this, we can sample correctly. We can take the samples to the lab. We can measure the permeability of a sample using either a constant or a falling head test. So if you think about a 2-foot high plexiglass tube with the sample in it, put water in at the top, measure the rate of flow of the water out. This gives you general measure of the permeability. When you're doing this, you have to be very careful about how you're sampling the material and how you're transporting it, because we're talking about coarse grain materials, and so the packing of those materials can change if not sampled and transported carefully. So you can get some wildly varying numbers of permeability depending on that. We have different field tests. We can put in piezometers that measure the in situ pore water pressures. And we see these usually in slopes and for landslides. Lysimeters are used to collect water out of the pore spaces. So think of the vadose zone. Looking at what minerals are in that water. And so these are being placed in Napa Valley to look at how the soils impact the taste of the wine that is produced. Tensiometers measure the suction, the soil matrix potential. So how much pressure is needed to suck out that water out of the pore spaces? And the information we get from that can tell the farmers when to irrigate, where they are on the drying or the wetting curve. Again, that's in the vadose zone. And then a perk test. I think of this as the Goldilocks test. So you dig a pit of a certain size and you put a certain amount of water and you see how fast it percolates through that pit. You don't want it to go too fast and you don't want it to go too slowly. You want it to go within a certain range, and then that will determine that the soil then is suitable for a septic system or leach field. And then pumping tests. We have a slug test or a Baylor test. This measures the hydraulic conductivity. Slug test is you put in this big metal slug and displace the water. Baylor test is you remove a known volume of water. The pump-in test measures the horizontal component of your hydraulic conductivity. So if you are getting a lot of inflow, then you have to pump harder to keep the water level at the same level. And if you don't have much inflow, then maybe you ease off on that pumping. Step drawdown test is used to come up with the test that is used to get the aquifer characteristics through the constant rate pumping test. So what we do is we pump at a certain rate, measure the drawdown, increase the pumping rate, drawdown increases, increase the pumping rate again, Drawdown increases till we get to a point where we don't have that relationship any longer. And that would be our optimum place to run for our pumping test. So let's look at a couple of these. The first one is the Tice method. And Tice measured with an infinite series the radial flow into a well. It's beyond the scope of the exam for you to solve one of these. It takes a while because you need a loose piece of paper, and you're not allowed to have a loose piece of paper in the exam. So the kinds of questions could be on the assumptions, or what is the form of the equation for transmissivity or storage? As shown here, you can see the circular nature of this. U depends on the radius, the storage, transmissivity, and the time. We need U to get the storage. So what we have is this loose piece of paper with a curve on it, and you're trying to match your data curve to that to get the U value and the well function of U value. Now, the other thing to note here, if you look at other textbooks, you will see different numbers. The numbers internally convert the units that are put in to the transmissivity and that you want to get out. And I think this is feet, let's see, this is feet squared per day units of transmissivity. But if it was gallons per day per foot units, then this would be a different number. So don't focus so much on the numbers, but look, you need the pumping rate Q, the well function of U, and the drawdown for the transmissivity. And for the storage, the value of transmissivity that you just calculated, the time, the U value, and the radius, or the distance of your observation well from the pumping well. Okay, so we're going to look at these numbers a little bit more clearly in the time drawdown method. So here we have a 24-hour pumping test. And we will draw our straight line relationship in through the points that are farthest away in time because they have settled down. You can see they're fluctuating a bit here till about 60 or 70 minutes. We extend that back to the zero drawdown axis and get that time. The second thing we need from this graph is the slope of the line, which is the change in drawdown that occurs in a log cycle. A log cycle is between 10 and 100, 20 to 200, 50 to 500, wherever it's convenient to come up with a log cycle. So if I go here at 1,000, I have 10 feet of drawdown. I go a log cycle away to 100, and I have just a little bit less than 6. So I have 4.15 feet for my change in drawdown. And that is what is used in this equation. But wait a minute. How can I put in the same values for the pumping rate and the change in drawdown and have different numbers here? Well, it's these numbers that convert the information you're putting in to the units that you want to measure, either feet squared per day or gallons per day per foot. So in the gallons per day per foot units, these are equations you often see in textbooks. I like the feet squared per day. I can remember 35 640 is the number of acres in a square mile. So those equations stick in my head more than these. So whatever you're used to, memorize one of these columns. What happens if you've memorized the feet squared per day equations and all of the answers are in the gallons per day per foot units? How do you convert? Do you remember that 7.48 conversion factor that was in that red box? Well, that is going to bring your 35 up to your 264. So again, you need to calculate your transmissivity and then use that value, your time intercept, and the distance of this observation well from the pumping well. Should never use values less than 10 minutes in time, since all of this fluctuation is going on. Distance drawdown is where we have a number of wells at different distances and one pumping well. So we need to go out and at the same time measure the drawdown. We extend that back to the zero drawdown axis to get the distance intercept, the R0. Time is the time when we measure. And the points that are farthest away in distance now are the least favorable to use to draw the straight line, because why? There's boundary conditions, there's other pumping wells, other things going on that can change where these points fall. Now for the equations, the numerator has doubled. 35 is now 70. 264 is now 528. We've exchanged the intercepts, the distance for the time, and the storage equations are essentially the same. So let's look at some examples. And I highly recommend this water supply paper 2220. It's linked from our website, and everything in there is appropriate for the exam. The only thing is that he uses the metric system, so you might need to practice converting from the metric to the English system, which is how the exam will be. All right, so here we have two wells. One is located within the Kona depression of the other. And as long as well A is pumping by itself, all of the water is coming in from the right and the left. But when well B starts pumping, its Kona depression intersects well A's, and at the highest point, it forms the divide. And the water will now be moving into well B that formerly went into well A. So when we have our data points that fall below our ideal curve, we have more drawdown than we would expect. That is due to well interference or some boundary condition, because you'll see this drop off right next to a boundary. What's the opposite case? We have less drawdown than we would expect. So we have some source of recharge or a leaky confining bed. And then what happens when we shut off the pump? So here we're pumping along and we're getting our drawdown, and eventually we don't get that nice relationship between the pumping rate and the drawdown. So we turn off the pump. The recovery in the well happens very quickly, and then it gradually comes back to the regional trend. So it's an inverse image rather than like a mirror image. And then this is kind of fun to do. If we are putting in a new well, and we want to make sure that we have enough drawdown, and we want to figure out the pumping rate. Let's start with what we have here. We're going to put in a well at 10,000 meters away. And at 200 gallons per minute, we have about 1 meter of drawdown. But I want to pump at 100 gallons per minute. So to get that, I'll take 2 points here, 4. Now take half of that, and 8 comes to 4, and I can draw in my 100 gallon per minute pumping rate, and I get less than a meter of drawdown. If I want to pump at 400, so 2 goes to 4, 6 goes to 12. There's my new curve. And here I would get about 2.5 meters of drawdown. So you can proportionalize any distance in between here, just given one curve. And then you can, if you put it in, you can see if you have accounted for all of the things that might be happening, like well interference or boundary conditions or a recharge source that's going to take this in a different direction. So this can be very useful if you're doing a site investigation and you want to put in a well at different distances. So again, these examples come from Heath, Water Supply Paper 2220, which is highly recommended. Okay, environmental. This is our last topic for today. And all of our references are going to be national references from the EPA. And if you're worried about all of the contaminants that are out there and how do I deal with them, which ones are important? Well, I looked at the substances priorities list, and the hazardous substances are put in this list based on 3 things: their frequency of occurrence, toxicity to humans, and the potential for humans to be exposed to them. So based on these 3 criteria, number 1 is arsenic, 2 is lead, 3 is mercury. So if you're thinking about man-made chemicals, the first 3 things on here are naturally occurring. And we will see tomorrow in the economic section, these are pretty important as we're looking for ore minerals. So they are, some of them are pretty widespread. Number 4 is vinyl chloride, which is a man-made chemical. Now, what we want to know is things like their properties, what are their MCL values, how do they affect our health, and so on. So we'll look at some of these in a minute from the drinking water standards, but I want to just mention where we have L-NAPLs and D-NAPLs. These are liquids that are lighter or denser than the density of water. And the things that are lighter than the density of water are going to float. And they are the components of gasoline, BTEX and MTBE. Everything else is going to be a D-NAPL. And so it's going to sink. going to be found in the below the water table. And there are a lot of acronyms in here. And the other way that you can use this table is to look at the contaminant source, because a problem might just say, I have a degreasing paint stripper plant, and you would need to know what would be the chemical, and therefore, as a DNAPL, how it would respond. So look at some of these dry cleaning plants are also ones that they might ask about, where we have PCE. TCE is also important, where we have vapor intrusion, as well as the DNAPL. Anyway, so looking at that can give you an idea of where to expect things. We don't need to worry about the water solubility values, but just knowing that they're lighter or denser than water. LNAPLs will migrate under the force of gravity, and if it reaches a clay lens, it'll move laterally until it can move downward again. And when it reaches the saturated zone, which would be the capillary fringe, the vapor phase is going to go away, leaving us with just three phases. Whereas the DNAPL, again, migrating vertically until it reaches those clay lenses, it's going to lose the vapor phase where it's saturated, and then it's going to continue to move on. So the stratigraphy becomes very important for the DNAPLs to get the orientation of any of those clay lenses or things that could divert the migration of the DNAPL away from where you might have expected it to go, but it didn't go there. Some other things to review quickly. TDS, total dissolved solids. We have 4 categories going up in units of magnitude here, order of magnitude, and fresh water up to 1,000 milligrams per liter. Anything above 500 is going to be not as good to drink, but they consider it fresh. And then within the saline category, we have seawater, which is about 35,000 parts per million or milligrams per liter. For the hardness, we're looking at the concentration of calcium carbonate in units of 60, and the difference between soft water and hard water, which is going to produce scale and staining. And usually at this level, it's going to be, if it's drinking water, it's going to be softened. And then we have all of these major environmental laws. And again, if you work in this area, you want to think of the national laws, not the state or local laws. First one being NEPA, and this requires our environmental impact statement. It was changed under the Trump administration to remove local input. So it's just the federal agencies coming down and doing whatever they want in a particular project, which is not going to make people very happy. So I don't know if that's been renewed or not. Safe Drinking Water Act. This is really important because it ensures our quality of drinking water. And so we have some of these programs, Sole Source Aquifer, Source Water Protection Program, Underground Injection Control under the Safe Drinking Water Act. Clean Water Act established industry standards. And the Water Quality Act is one that requires the permits, the NPDES permits, to regulate point source discharges. RCRA and CERCLA, and then an amendment to CERCLA where brownfields were defined. And so here, if you think of brownfields as areas within a more developed place, like urban areas, so we want to clean up that property and reuse it rather than going out to open space and leaving the contamination without being cleaned up. Toxic Substances Control Act looks at PCBs, asbestos, radon, and lead-based paint. Oil Pollution Act looked at catastrophic oil spills, and we saw in the Deepwater Horizon oil spill in the Gulf that the Coast Guard worked offshore and the EPA worked onshore to clean that up, which is taking a long time, has taken a long time. And then our only, well, maybe not our only, but one of the few mining laws that we have, Surface Mining Control and Reclamation, which is supposed to protect us from the adverse effects of mining. It's not enforced by the EPA, it's enforced by the Department of Interior. So we'll see in the economic section tomorrow how well this law is doing. So question, what kind of questions could they ask about environmental laws? Well, they could give you a bunch of acronyms, SDWA, RCRA, NEPA, CWA, and say which one of these has the wellhead protection program, or when dealing with underground injection control, which of these laws does this fall under? That sort of thing. And I find that using the acronyms makes it a little bit harder to remember all of these, because safe drinking water sounds a little bit like clean water and water quality. So that's the sort of thing that could get into. Again, not very many questions on this sort of thing, but just want to cover the major ones. And then there are all these regulations pertaining to drinking water standards, underground storage tanks, injection wells, and we've already talked about safety regulations. So there are also guidance documents which are non-enforceable. And I want to talk about this one here, on-site wastewater treatment, for a minute. So let's look at our drinking water standards. Inorganic chemicals, picked out a few here, organic chemicals. Now, number one on the SPL list was arsenic, number 2 was lead, number 3 was mercury. They cause different health problems. So the MCL, which is the maximum contaminant level, so we're going to use that term a lot, MCL, is our goalpost. So we want to have no more than that in our drinking water. We also want to look at nitrate, particularly across the country where we have farming. And sources of nitrate are sewage, our leach systems, and feedlots, places like that, or applying excess fertilizer. With our MCL of 10, if we drink water with these high levels of nitrate, babies can get methemoglobinemia. which is also called blue baby syndrome. Blue baby syndrome, these babies can die because the nitrate gets into the bloodstream and robs the oxygen out of the hemoglobin. So they can't oxygenate, they can't breathe, they'll turn blue and they'll die. Whereas adults, they can get sick from this, but they usually don't die because we're bigger. So nitrate's very important to make sure we catch and mitigate. For the organic chemicals, here's vinyl chloride, 0.002 MCl, and these others have 0.005, except for dioxin. 7 zeros to the right of the decimal place for its maximum contaminant level. So I would know some of these just to get sort of a baseline. And then all of these cause cancer, so organic chemicals are a problem. Secondary drinking water standards are non-enforceable at the national level. They pertain to odor and taste. And saltiness, iron, manganese, total dissolved solids, 500. Remember I said fresh water was up to 1,000 milligrams per liter, but anything over 500 is not going to give us very good drinking water. So these are non-enforceable, so I wouldn't worry about these so much. Just take a review of them and see what kinds of things you find on this list. And then the on-site wastewater treatment systems. These are leach fields or septic systems. And we have a guidance manual that provides us with a lot of technical information that's very helpful. We have some of the things that we want to look at are the daily volumes. What are the pollutants we're putting in? What's the peak flow? How do we minimize the flows? And then what happens in the environment as these things are formed or move through the environment? Can the receiving environment clean them up? So if we look at this map of the US, although this is an older map, basically we have many, many states that depend on these types of systems. And so the things that we need to look at as our human waste goes in is parasites, bacteria, and viruses. Now, viruses generally don't get mitigated. They tend to persist in the environment, whereas bacteria can be filtered out. Whether we had hard or soft water, any organic compounds or metals, phosphorus from cleaning products, nitrates that we could form, and pharmaceuticals. And this is an emerging area of concern with all of the new products and how they respond in the environment. If you just take, for example, insulin, it's a hormone, and with 20% of the population having diabetes, we're excreting that insulin and gets into the water, and the fish in the Chesapeake Bay have the characteristics of both male and female from the high levels of hormones. These are not being filtered out from our leach fields. So that could be a future concern. So here's a little diagram showing you the drain field. And so it depends on the soil's ability to infiltrate and degrade the material we're putting in. So things like our fecal matter, surfactants are generally removed within 5 feet. And that's why if you have 5 feet between the leach field and the groundwater, usually that was considered enough freeboard to filter out our human waste? Well, we have floods. We, as I mentioned, are putting in other things into these drain fields. Phosphorus is kind of interesting because if we have karst topography and it gets into the surface water, we can get algal blooms, and that is not good. And then nitrates. Nitrification occurs with oxygen, and it takes the ammonium nitrogen from the urine to nitrite, and then the bacteria take it into nitrate. And the nitrates are not removed. And so what we have to do is mitigate against that. And we do that by a particular kind of bacteria that can convert the nitrate plume into gas that can be removed. And there's the question here, what is a water contaminant free agent? I'm not sure I could answer that question right now. If you tell me where you saw it in the study manual, I might be able to. I'm kind of drawing a blank on that right now. So.
Okay. Oops, wrong thing. There we go. Last few little tidbits here before we go home for the day or go do something else for the day, since we're all probably at home anyway. We have several questions beginning on page 12 or 13, excuse me, in the course notes, and I just want to talk through some of this stuff. The contours that we have here are contours of groundwater levels. And so what we have in this, there's no topography here. What we have in here is you saw this diagram before. The curvy lines are the unconfined aquifer water levels, and they mimic the ground surface. So a question about this might be, describe the ground surface, or where would water be inclined to flow at the ground surface here? And obviously that's going to be straight down the middle if it's following the topography, because we have a little bit of a valley down the middle in the groundwater, which mimics the surface. And then we've got all these straight lines that are confined aquifers, and there are two of those that are divided by a groundwater barrier. Contouring, this is kind of just a contouring problem. Contouring is contouring. It doesn't matter what you're contouring. If we are contouring topography, we are all pretty much familiar with that. Water this is a good example of that. Thickness of things, ore values. A lot of times the ore values are contoured on a excuse me, fence diagram, which is kind of a three-dimensional drawing where they're put together with a whole series of cross sections, and that is done so that you can follow the richest ore based on assay values that have been taken in the underground from core samples, for example. Contaminants, which is what this problem is about, depths of things, it's all the same thing. You're connecting points of equal value and bracketing points of like values. So when I take the data that's given here, I've got 6 boreholes. There are far more boreholes than there are listed. And all that may mean is that the water wasn't tested there. Or they sealed the upper aquifer and they have been using only the lower aquifer. So since this is a contaminant that's at the surface, then the lower aquifer has no contaminants in it. But when we plot the benzene levels at these various boreholes that we have listed, and I connect my points of equal value and bracket points of like values, I get something that looks like this. Yours isn't going to look exactly like this. Yours is going to look a little bit different. And everybody draws this a little bit differently. And so the question that it's asking here is, where are we going to drill next to determine the lateral extent of the contaminants? To me, lateral extent means everything out in a generally horizontal direction from the source. So the way I've drawn this, I would select B because it's beyond where the last contour that I put here was for the lowest level of contamination. If I was a glacial geologist, I might select D. D is on the side of the valley, and for excuse me, glacial geologists, lateral moraines run down the side of the valley. So lateral to them means down the side of the valley. So we have put both answers as possibilities here. You could also very easily have drawn this line and just tucked it inside D. And then you've got two possible correct answers. And it's not uncommon on the exam for that sort of a situation to exist, as well as having no good answer. And so it can be quite frustrating when you're trying to figure out the answers to the questions. So just keep all that in mind. I would make a comment about this question because it's a little bit ambiguous. And then the next questions, which are on the following page, on page 14, you're given at the top of page 14 in the practice questions section of the course notes, you're getting a story. And it talks about PCE. And they say that it's found at a large dry cleaning plant. Well, they could have just said dry cleaning plant, and they would have expected you to know that it is a DNAPL, just like the PCE is a DNAPL. So that's one piece of information. Then it has all this, the tank location and the elevations to a bed that's in the subsurface. Now this series of questions about this could have started out with, what's the strike and dip of this bed? Because you have the 3 different elevations given to you at the locations given in the coordinate system. Now, one thing I want to talk about just briefly about this coordinate system is that oftentimes when we are working with coordinate systems, we tend to make the y-axis be on the left side and the x-axis be on the bottom, and then all the numbers increase moving up from the horizontal axis and moving to the east of the y-axis. And that's not true when we have this coordinate system. And in this particular case, it is true for the northerly numbers. They are increasing from a east-west baseline down here somewhere. But the westerly numbers are increasing to the west, which means that they're increasing in the if we had a standard XY with 0 located at the intersection, then these would be increasing to the left of that y-axis as opposed to the right. And so a lot of people will confuse these and not really think about what that W means. That means westerly, which means that it is increasing to the west of some north-south baseline over here. And if you do that and it asks what the strike and dip is going to be, you're going to get a mirror image for the strike and dip. And it will be the wrong answer, and it will be an answer that's provided. So just be careful with that. Northerly numbers increase to the north, westerly numbers increase to the west, southerly numbers increase to the south, and it's the easterly numbers that increase to the east along the x-axis. So we have located our points on here in the coordinate system once we've laid it out properly. The slope is sloping down to the south-southwest, so I did a cross-section to the south-southwest, and that happens to be perpendicular to strike, which we are not solving for strike and dip here, and it's given to you. If that's not part of what they want you to be working with, then they will generally make things a little bit easier, like making this direction perpendicular to strike. It also happens to go through the location that borehole A is located in. Now, I drew my strike line in there it was given, and I drew it in there so that I was understood where things were, what the situation was. I'm a visual learner, so I always have to draw things. I can't just read that story and say, oh, well, that's obvious, because it's not to me. And so I drew the dip direction. It's dipping to the northeast where the low point is. And I drew the dip angle in there so that I was sure which direction it was dipping, because it's always dipping in the direction that it opens up. And then I started in with my cross section. The cross section has a slope to it. It's a 20% grade. So engineers and engineering geologists talk about slopes, whether they're cut slopes or fill slopes or road grades or whatever, they're in percent grade. And what that means is gradient after you take the percentage sign away and move the decimal place over two locations. So 20% grade in hydro speak is going to be a 0.2 gradient. So just to help keep that clear in your head, if you've never done engineering geology, that's the only difference, is that you have turned this percentage into a decimal number. So I've got a slope, 20% grade or 0.2 gradient, and it talks about the confining layer, or the recharge area, I should say, for the confined aquifer. That means the stuff that's underneath our claystone layer is 500 feet down. That's 20% grade. The depth to the groundwater is 40 feet under the site, but because our claystone is dipping here and it's 30 feet thick and it's higher towards the ground surface, as we get farther down slope, the water's going to pile up on top of it and it's not going to have anywhere to go. So we have a seep coming out of the ground, a spring, if you will, coming out of the ground right where the top of the claystone thickness is intersecting the ground. So I draw my depth to water in here, and the questions asking where, first question 57 is where you're going to find the contaminants in the unconfined aquifer. So that means this space here above the claystone layer. And that space, if this was a DNAPL, which it is, that question is kind of asking two things. One, do you understand this is a LNAPL or a DNAPL? And the other one is, do you understand groundwater flow? If we are thinking about this just being a DNAPL, it'd go straight down until it hit the claystone, and then it would turn and move down the slope of the through the force of gravity because it's denser. If we incorporate the principles of groundwater flow, then it's still going to be vertical through the vadose zone here, the part above the water table. But as soon as it hits that water table, it's going to move, and it's going to still be coming down through the force of gravity, but it's also going to be moving down gradient because of the groundwater flow. Now, the one thing that I haven't mentioned here is that there are a number of layers of clay lenses. Doesn't say where they are, doesn't say how deep they are, doesn't say how thick they are, doesn't say how laterally extensive they are. All these things that would make me crazy if I didn't know, if I was trying to give an educated answer to something. So when I throw a few clay lenses in there, it kind of messes things up a bit. But when it hits the top of that clay lens, it's going to travel along it until it can, because it won't go through, until it can travel down again. And if we get to a clay lens that's tilted against the slope, it's going to travel through gravity that direction and through groundwater flow the other direction. So we will have it sort of permeating this whole entire area if it's been very long. And it's hard for them to ask questions that aren't just kind of general, but it's hard for me to answer questions that are so general, because they're asking questions that you might want to give a very specific answer for and you can't. And it makes me crazy. But anyway, so the second question is asking, where would it be possible for these contaminants to enter the confined aquifer, which is down here underneath the claystone layer? So we've got B that's projected here, and I only used B to determine where the claystone thickness was because it was a long parallel to strike, so it would be the same depth where it intersected the cross section. But B is uphill, and so it's not going to move cross hill or uphill very much. It's going to flow downhill because 20% grade is pretty steep. So that's just in here to locate this claystone lens. Borehole A is here and we don't know much about it. When I first put this question together, I was thinking, okay, so it's probably seeping out here at the ground surface, traveling overland, which would be what, 33, 35 feet, the hypotenuse on a triangle here. And then it would be entering down below the claystone, intersecting the ground surface. And that was, to me, was the most logical answer, given the information that I had. But that was not an answer choice. And so sometimes you're going to find that the most logical answer, the one that comes to mind when you read the question, is not an answer choice for you, which that's another thing that makes me crazy when they don't put out what the most logical answer is to choose from, and you have to choose from some other answers. Borehole A doesn't say how deep it is, doesn't say when it was drilled, it doesn't say whether it's cased, it doesn't say whether it was sealed properly. When was it drilled? 1857, you still get water out of it with a bucket. Was it drilled in 1972 by a geotechnical firm who just threw all the cuttings back in the hole and put some grass seed down and called it done? Was it drilled last week and somebody actually pays attention to the current rules and regulations about abandoning wells, abandoning boreholes? Don't know. But that's the most logical choice from the choices that we have. And directly under the site, there's no evidence for there being any breach in that claystone layer to allow contaminants to get through it. Question number 59 is asking about remediation. So let's talk about remediation for a second here. There are a number of technologies. This table is in your study manual. And this table has rankings according to expense. And sometimes they have questions that say, what is the cheapest way to fix this problem? And they describe a problem. Well, I know your clients are asking the cheapest way to fix things. They're not going to ask you what's the most expensive way. They might ask you what's the most efficient way or what is the easiest way or something, but they're not going to ask you about expense. And the most efficient way and the easiest way are usually going to be on the low end of the expense. So as you're looking at the table that's in the study manual, it's a lot more elaborate than this framework we've got here. But think about those that have a low or a I, low to intermediate expense level as possible solutions for your problem. And then we have another table in the study manual that elaborates on this information. And these are some of the common remediation methods. So SVE methods, the air sparging and bioslurping, they will sometimes have those terms on the exam. I guess they kind of like those terms, but you don't do SVE with methods with DNAPLs because they sink. And this is only for the stuff that's up at the top. So thinking about those, take a look at these and see when and why you would want to use some of this stuff as possible options. So looking back at our site and thinking about the question, how are we going to remediate this? Well, if you have a leaking underground storage tank, what's the first thing you do? You remove the tank. You yank the tank, and then you take with it the most contaminated soils immediately adjacent to where the leak was. So 2 of our answers we can throw out because they don't say take the tank out, and taking the tank out is what you always do when you have a leaky tank. So we're down to 2 answers, and then thinking about the other 2 answers, we kind of need more information that we don't have to be able to actually make a complete judgment call on this. What happens is that any of these clay lenses, if we knew how big they were, thick, laterally extensive, impermeable, shallow, all those things we don't know, if it was relatively shallow and it was contained, for example, within this upper clay lens, you could put a slurry wall down to that clay lens and contain it and treat it there. And then you would go from there. But we don't have enough information to be able to definitively isolate it at a shallow depth, because a slurry wall cannot be put in all the way down from the tank site to the claystone thickness. That's about 300 feet, and that is not really a viable solution. So that by default kind of leaves us with the last answer, because we don't have enough information to really make a call on a slurry wall. Would you extract tank contents before removing the tank? I don't know the answer to that question because I've never done contaminant stuff, but I believe so. The question number 58, why is A the best answer? Because the borehole penetrates the clay layer. Well, out of the choices that we have, borehole B is not a viable answer because it's uphill of the site. And there isn't any reason to believe that the contaminants wouldn't reach the confined aquifer. That's not, we don't have enough information to determine that they wouldn't. Directly under the site, it's not going to be there because there is no boreholes there. The claystone thickness is dipping. So that would be an unlikely choice. And it doesn't say much about A, but A is directly down gradient from the leaking tank and down the hill. So that's why borehole A would be the most likely solution. Somebody says here, I bet they'd include both of those options: extract contents, remove tank. Geo questions are plagued with ambiguity. That is true. Geo questions are plagued with ambiguity, and particularly on this exam, they are plagued with ambiguity because they often don't give you enough information to be able to answer it appropriately. And that's what makes me crazy. So one other thing I want to say here is about soil vapor extraction, because they tend to like those terms. These are for fuels and volatile organics in the vadose zone. So these are the LNAPLs, and it removes the volatiles by vaporizing and allowing them to escape through the soil. The process itself will promote in situ bioremediation. It works best in permeable and porous soils. So you have to have a pretty good handle on the soil structure and stratification, because if the vapors can't escape, then the volatiles can't escape. Then if there's a clay lens in there, the volatiles can't escape, and so it won't work. Also, soil moisture reduces the effectiveness of these methods, and so if you have shallow groundwater, it could be more difficult, so it's less desirable. Okay, that's a lot of stuff today. We will stick around for a few minutes if you have specific questions, and if not, and if a few people are just sticking around to see if anybody else has questions, then we will be shutting it down. So questions we will answer. You can wait until tomorrow and save questions for tomorrow, write them down, and we can talk about